its norm on K is bounded by tau plus epsilon raised to power n. Not for every n, for every sufficiently big n. Of course, because it's just we need to have tau n smaller than tau plus epsilon. And in particular, well, let me say it like this. Now assume that the transfinite diameter is strictly smaller than 1. Then, again, for n bigger than some sufficiently big n, well, of course, epsilon, and we should probably put k. There exists a monic polynomial with coefficients in C such that, oh, well, why do I need epsilon? I don't think I need epsilon here. Such that the norm of P is strictly smaller than 1. So on transfinite diameter, on compacts with transfinite diameter smaller than 1, we can find for all big degrees monic polynomials which take all values smaller than 1. So for every so this follows immediately from the definition of the transfinite diameter. Now, if assume further that K is symmetric with respect to the x-axis, which means that if Z is in K, then the conjugate is also in K. Then we can take such a polynomial with real coefficients. Oh, let me put it like this. Monic of degree n. Such that P, norm of P is smaller than 1. Well, it's clear why, because if we have a polynomial with complex coefficients with this property, then its real part, its norm of the norm of its real part will be less or equal than the norm of P. So if then and write P of Z as U of Z plus I V of Z with both real polynomials. Well, clear that real polynomials. Then clearly the norm of U on K is less or equal than the norm of P on K, which is exactly the norm of U plus, no, I don't think so. Well, it's basically clear. And this is exactly because our K is symmetric with respect to the x-axis. So we can find, if for symmetric K, we can find polynomial with real coefficients and of K norm 1. And theorem of Fekete and Segue. In a wonderful article of 55, very influential, very important article of 55. They obtained several important results in this article. And the first of them is the following, that actually we can find such a polynomial with integral coefficients. So K compact tau of K less than 1, and K is symmetric with respect to the x-axis. Then there exists monic let me put it like this, then for n sufficiently big, there exists monic polynomial monic of degree n and with coefficients in z such that strictly smaller than 1. Well, now in the modern literature, this is usually proved using arithmetic Hilbert-Samuel inequality. So basically using some kind of lattice argument. And what is lost? Use what is called arithmetic Hilbert-Samuel. What is lost in these proofs is monic. So as much as I know, one cannot prove this using this Arakelov kind of argument. One cannot obtain monic polynomials. Well, actually, for our applications, we don't need P to be monic. So for our applications, just any P would do. I think proofs using arithmetic Hilbert-Samuel can be found in literature. Particularly, there is a very recently appeared or not yet appeared book on Rakelov theory, edited by Sule, maybe some other people, where there is a note by Pascal Utissier where he gives very laconic exposition of this stuff. But I would prefer to give the classical kind of proof. Basically the proof from the Fekete-Segue article. I find it's also kind of compactness argument. And I personally find it very appealing, and I think I would be happy to show it to people. So okay. So there will be two lemmas preceding and the first lemma will be needed only for the second lemma. So I will now state the second lemma that I will call main lemma. And I will show how the statement follows from this main lemma, and then I will return to the proof of the lemmas. So maybe I start a new slide. So main lemma, and it will be kind of lemma 2 because it will follow from set and lemma 1. Yeah. Now epsilon will be just arbitrary positive real number, well, small real number. And well, let m be sufficiently big integer. I will specify during the proof what it means sufficiently big. Then, for every n bigger than m, also integer, there exist polynomials Pn and Qn, Pn with coefficients in Z and Qn with coefficients in R. With the following properties. First, Pn is monic of degree n. Second, the degree of Q is smaller than m. So you see what happens. P is has integral coefficients and big degree. Q is not so good, it has only real coefficients, but it has a small degree. And not only small degree, it also has small coefficients. The coefficients of Q belong to interval -1/2, 1/2. So they are really small bounded coefficients. And finally, P and Q are very close to each other on our compact. So they, on our compact, they are of distance smaller than epsilon. So if we take their difference, we obtain a polynomial which takes very, very small values on our compact. So let me perhaps just show it's a bit longer, the statement of the lemma. So let me. Is it visible like this, or it is too small?
No, it's too small.
Too small. Okay.
This is
then I have to show it just in, okay. Like this is okay.
This is okay.
Yeah. Okay. No, I will not continue writing like this. I will return to the previous size, but I just want to show you the full statement because it is a bit is a bit long.
That Qn is Q, right? Qn is Q, right?
Sorry?
That Qn is Q, right? Yeah. On the last line. For Qn is Q, right? Just Q.
Yes, Qn, yes.
Below?
Yes, and Pn.
In the condition 2, is it degree of Qn is less than m or less than n?
M, small.
M.
Consider M as fixed, but n is varying.
Okay.
Okay?
No, what is Q, Yuri, what is Qn? I'm not getting, is Q, right? Just one Q, right?
Qn, yes. No. It's both cases Qn.
No, Q subscript n or?
It will
Q
depend.
subscript n. There are two polynomials. Q. Oh my God. Yeah.
Sorry. Okay.
Yeah.
Okay, sure.
Okay.
Yuri, sorry to interrupt. Is there a hypothesis on K in this lemma, the same as the main theorem?
Yeah, same hypothesis. Yes. Okay. Sorry, I had to say it. Okay, I will. Yes. You see, this is why I show. Yes. So let me edit K compact of transfinite diameter smaller than 1 and symmetric with respect to x-axis. Okay. Okay, so here is too big, like this. Okay. Okay, so here, this is the statement. And now, let me show that this main lemma implies the theorem. Yeah. So we have our Qn's. We have infinitely many Qn's. But they are, they're compact. So the set of polynomials of degree smaller than m and with coefficients in minus 1/2 is compact. And this implies that that Qn's accumulate somewhere. So this means that there exists n1 and n2 with n1 bigger than n2, such that the norm of the difference Qn1 and Qn2 is smaller than epsilon. Now let us compare Pn1 minus Pn2. It is bounded by what? By Pn1 minus Qn1 plus Pn2 minus Qn2 and plus Qn1 minus Qn2. And all of these guys are epsilons, right? All the three. These are simply by our construction. And this is epsilon by the choice of n1 and n2. So it is smaller than 3 epsilon. And clearly the difference Pn1 minus Pn2 is a monic polynomial of degree n1. Degree n1 and has coefficients in z. And so we're done because we just choose epsilon small enough and we obtain, so let's call this P. And say choosing epsilon like I don't know, 1/4. We're done. So main lemma easily implies the theorem. And so we are left to prove the main lemma. First, well, as I said, it will be lemma 2. So I will start with lemma 1. So we have same hypothesis. Okay. Then there exists some gamma, some just positive gamma, and some rho. And rho is not just positive number, is between 0 and 1. So it is crucial that rho is smaller than 1. And the sequence of polynomials Fn of z such that Fn, each of n has real coefficients, monic, are they really? No, I'm sorry, I denoted them un. Monic, and has norm which grows exponentially, which decreases exponentially to 0. Norm bounded by gamma times rho to the n. So we have polynomials with growing degrees, all monic, with real coefficients, and with norms exponentially decreasing norms. Yeah. Question? No? And the proof basically it follows from the definitions, so it's not very hard. So as we have seen in the beginning, there exists some T of Z monic well, with real coefficients. Monic. And with norm smaller than 1. So let's L be the degree of this T. So it is just definition of L. L is defined as the degree of the T. Let's write it like this. So the T of Z is Z raised to power L plus further terms. Now take arbitrary N and do the Euclidean division. We already did it in the previous lecture. LQ plus R. And define UN of Z simply as the qth power of our T. Well, this will give us a polynomial of degree LQ, and we need R. So let us add, for instance, Z to R. We again obtain monic polynomial. And if we denote rho as the norm of T, well, qth root of the norm of T, sorry, what qth root? Lth root. And well, gamma just to take care of all the rubbish. So we will see what will be gamma. Then what we obtain that the norm of UN is what? Is, well, it will be the norm of T. Q times the norm of Z to R, or it is what? It is rho to LQ norm of Z R, and then it will be rho to N finally, which is LQ plus R. And so this will be our gamma. Let me put it L minus. So maximum of this 1 raised to the power L minus 1. So it will be like this. And so it is bounded by gamma rho. So well done. Okay, so this is the proof of the first lemma. So it's easy. We basically take one polynomial and take its powers, and we should slightly correct them. So, yeah. Now the proof of lemma 2 that I'm going to state, I will remind the statement, is much a bit more sophisticated. So let me remind again the statement of lemma 2. Which is main lemma. So same hypothesis on K. Yeah, and epsilon some positive number, and M bigger than certain M0 that will be specified. Not that I will specify M0, but I will say how it should be defined. Then there exist, then for every n bigger than M, there exist Pn of Z with coefficients in Z, Qn of Z with coefficients in R, and with the following properties. First, Pn of Z monic of degree n. Second, the degree of Qn is smaller than m. Third, coefficients of Qn, the coefficients of Qn belong to the interval -1/2, 1/2. And fourth, Pn and Qn are very close on our compact. Smaller than epsilon. Looks like I have to, yes. So,
Yuri,
yes.
can I ask some question?
Yes, of course. Yeah.
I am.
Yes, it disappeared, probably disappeared my.
No, it is about the lemma one. In fact, completely at the beginning of the talk, you had constructed a sequence of polynomials. The norm on K was smaller than tau plus epsilon to the power n, with
Yes.
tau strictly smaller than 1.
Yes.
Why did this sequence of polynomial not satisfy the conclusion of lemma 1?
Wait a moment. Good question.
Of course, they were not real, but if
no, but you can make them. Yes,
you can make them real, yes, by the argument that you gave.
Yes, you can actually make them real. Yeah, maybe you are right, but wait a moment. Okay, maybe you are right. So, which means that first lemma will probably not need it, and so which means that I did not think it well.
Okay, we can discuss this later.
We can discuss it later, yes. But anyway, first lemma is not what makes problem. First lemma is really easy. It is the second lemma which is kind of intricate a bit. And it seems that I have to restart my screen because it's already too hot and it doesn't want to work. Ah, no, it works. Okay, then I will restart it later. Okay. And the proof, well, they credit the argument, Fekete and Sego credit this argument to Kakeya. Well, I don't know which exactly work of Kakeya. it goes back to, but well, this is what Fekete and Segyo tell us in their in their article. So according to Fekete and Segyo, it starts again being So here is the proof. Okay, so for the time being, I fix M, and then at the right moment, I will see which conditions have to be imposed upon this M. And let N be bigger than M. Then we have a polynomial Un of z, and we will write it like this: z to the n plus, well, the coefficients, I will make them with tildes, bn minus 1 z, oh sorry, bn minus 1 zn minus 1 plus etc. So the coefficients will be with tildes. And so, and this UN is exactly from, is from lemma 1. So UN has norm smaller than gamma rho n. Now let us take UN minus 1. It starts from Zn minus 1 and then other terms. And what we can do, we can simply use this polynomial to correct the coefficient b is real, but I want to replace it by the nearest integer. So I just use UN minus 1 to do it. There exists some lambda n minus 1 in my 1/2, such that if we take UN minus lambda UN minus 1, then it will be what? It will be z to the n plus, and now I will write without tilde, and this will be already an integer. So it will be simply the nearest integer to bn tilde. And then go other coefficients which are not, which may be still real. Coefficients are still in R. But we corrected one coefficient. We corrected coefficient bn minus 1, made it in Z, and we did not do a big change. We just subtracted this multiplied by some relatively small number between -1/2 and 1/2. Okay, but we can now continue this procedure and find lambda n minus 2, etc., lambda m, all in the interval 1/2, 1/2, -1/2, 1/2, such that the polynomial un of z minus lambda n minus 1 un minus 1 minus etc. minus lambda m um has coefficients of degrees, well, which degrees? N minus 1, n minus 2 until degree m in z. So coefficients until degree m are in z, coefficients of lower degrees are still in R. So call it capital V. Okay, call it Vn. So we write it like this: Zn plus some Cn minus 1, Zn minus 1, Cm Zm, and plus what is left. Cm minus 1, but here I put tilde. And so these coefficients are in Z. Until here. And these coefficients are in R. It is C, it is not tau. So we are almost there. And now what we do, we simply correct the remaining m coefficients. We just replace them by replace Cm minus 1 tilde, C0 tilde by nearest integers. By their nearest integers. Call them Cm minus 1, C0. What we obtain? We obtain some polynomial, Pn, n minus 1, Zn minus 1, plus etc. plus C0 in Z. And what we did, we just modified the coefficients of degrees smaller than m. So we take Qn is, accumulating the mistakes we made. It will be C m minus 1 tilde minus Cm minus 1 plus etc. plus C0 tilde minus C0.
It is the opposite.
Or is the opposite? No, I want to take the difference. Ah,
Yes.
yes. Yes, you want to take the difference, then it will be the opposite. Yes, I agree. Yes. And so this is in R of Z. And Pn minus Qn will be this Vn. Okay. And what is left is to estimate the norm of Vn. So we obtained P and Qn, we see that their norm is Vn, and now we want to estimate their norm. So let us and what was Vn? Vn was Un minus lambda n minus 1 Un minus 1 minus etc. minus lambda m um. And you remember that U's have norms decreasing exponentially. Use letter K here because M and N are already occupied. And this means that simply that the norm of Vn is bounded, well, by the norms of all these guys. Well, and lambdas are an absolute value at most 1/2. Well, I'm not going to really use this 1/2. I will just use 1. So and now our favorite trick with the sum of geometric progression, something that we teach our first year students, and they always are amused that things wrap up nicely like this. So it is bounded by gamma over 1 minus rho m. And now we define m. Now it's the time. So define m to have this smaller than epsilon. And this completes the proof of the second lemma and also of the theorem of Poea. So, okay, this is how it is done. Well, I think argument is quite intricate. I would be happy to see a kind of less tricky form of this argument using some general stuff like compactness, but without going too much into Arakelov theory. So, but I could not, well, this is what I could produce myself. So I'm not completely satisfied. I would like to have something more elegant than this argument. But this is what we have. Okay, any questions on this argument? Okay, if there are no questions, then we can switch to the theorem of Poea. Let me remind you, theorem of Poea. Again, K, same hypothesis on K. Sorry. Means symmetric with respect to x-axis and and of transfinite diameter smaller than 1. And we denote delta as the complement of k in the extended complex plane. So infinity is also here. And I will assume that delta is simply connected. I think this hypothesis is not needed, but it will be simply easier for me to give a proof. Simply. Now, f is a function regular holomorphic on delta. And at infinity, well, including infinity,
just one small question. If you take your compact K and you fill the holes, don't you get the same tau value?
I think that, what do you mean by fill?
You add to the compact all the bounded components of the complementary. By the maximum principle, the norm of P on of any polynomial on K or on K field is the same.
Probably, but you see, I don't want to make some blunt statements right now because, well, you see, it's very easy to make a mistake in complex analysis.
Okay.
And
fine.
I feel, you see, it happened to me to make totally dumb mistakes in complex analysis in my articles.
Okay.
So I'm really trying to be very careful with all these
Perfect.
complex. Yes, you see, it is. So probably you are right. It's very possible that you are right, but I prefer not to make any. Well, in this form, it is totally suitable for me. So I prefer to state it like this. But very probably you are right. Yeah.
Fine.
Yeah. And its Taylor at infinity has integral coefficients. Coefficients in Z. So we write it f of Z as A0 plus A1 over Z plus A2 over Z squared plus etc. And with all these A0, well, let me just write it briefly. And this is simply, well, power series with coefficients in Z. Then f is rational. So what we assume, two crucial, well, actually three crucial things. First, that the transfinite diameter is strictly smaller than 1. It's no longer true when transfinite diameter is 1. Just take as K the closed unit disk, and you can construct plenty of series with integral coefficients who are not rational and who are holomorphic in this in the complement of the closed unit disk. Second, it also must be symmetric. Well, this is simply, well, since we deal with reals and so on, we must expect it to be symmetric. And third, that the coefficients are integral. Well, so this is so these are three crucial assumptions, and with these assumptions, can be only rational function. Okay, so let me try to prove the theorem now. I have like maybe 20 something minutes left, so but I think it must be enough. I will use an argument that I actually learned from Veselin Dimitrov's talk that he gave in Warsaw. I want to thank most warmly Masha Vlasenko. I'm not sure that she's present today, who just notified me that such a talk would take place, and Veselin himself, who did it. But Veselin credits it to Raphael Robinson, though I was not able to follow Robinson's article, but I presume that it is the proof due to Raphael Robinson. Well, Raphael Robinson is most mainly famous as the husband of Julia Robinson, who was much more famous than him, a celebrated logician, but he was on his own a decent mathematician, did some work like capacity theory, complex analysis, algebraic number theory, and so on. Okay. So again, by Fekete-Seger, implies that there exists a polynomial which is one, which is with norm on our K bounded strictly smaller than 1. Now let us take our K. Let for instance like this be our K. Let this be our K. And we can take a contour around K like this. So this is K and this is our contour C. A contour C around K. Oh, I tried to make it like script letter, but it really looks bad. Let me just write it normal C around K. And so close to K that on C our polynomial is also small. That also the norm of P on C is smaller than 1. It's clearly can be done by compactness. Okay, let us write our P. So it will be a polynomial of degree, certain degree D. And let M be so big that, well, some strange inequality, we will see what it means in the proof, that, well, we have the following. The norm of P on our contour raised to the power M times the norm of our function f on this contour, f is well defined on the contour, times the norm of the function z on this contour raised to the power, let me put it like this. The maximum of norm of z and 1 on this contour raised to the power d minus 1 and times one more strange thing, the length of our contour divided by 2 pi, and all this we want to be smaller than 1. And we can always achieve it because this one is kind of constant, and m, and this we raise to some small number to power m, so with big M we can always achieve it. So m is a very big number, and I'm going to prove that under this condition, P of z m, let us note this condition star. P of z m f of z, we will prove that it belongs to, it is just a polynomial. So the denominator of f is here. So we multiply by suitable power of p and we obtain a polynomial. Okay, let us write Taylor at infinity of this p of mz. P of z m f of z. We have some terms of some positive powers of z, or non-negative, let us call it non-negative powers of z. And plus come the negative powers, some b1 over z plus b2 over z squared plus etc. And what we want to show, and all them belong to integers, because, well, this is integral polynomial, this function has integral coefficients, so all these bi's are in z, yeah. And we want to show that these bi's actually vanish. So there is no negative part, only positive powers, and then we're done. All zeros. And well, to start with, we show that the first d coefficients vanish. So b1 equal to bd vanish. Where d, I recall, d was the degree of our polynomial. And this is just the Cauchy integration. What is this? It is integral on our contour of p of zm f of z, and we should multiply by z to the power k minus 1 dz. And by just by our condition, look, well, in our condition, we took care of everything. So this is a condition that with this condition, when if we estimate this integral just in the usual, just most naive way, condition star implies that bk is smaller than 1 for k equal to 1 until d. And, well, we use, well, what I call the main principle of the F-anten analysis. So if an integer is smaller than 1 in absolute value, then it is 0. So bk must be 0. Yeah, this is until d. So we have the expansion. P raised to power m times f. Again, the expansion will be terms of, so positive powers of z, or non-negative powers. Problem is that in France, I already get used to the French convention that 0 is a positive number. But I think it's only French convention, and well, 0 is not considered a positive number outside France, so one should say non-negative here. Non-negative powers of that. And plus, then we have no coefficients until d, but then coming coefficients b d plus 1 over z d plus 1, and etc. Yeah. But no terms. No terms 1 over z until 1 over zd. How we deal with now? We simply take multiply by 1 more power of p. We take p of z m plus 1 f of z. And again, this will be the non-negative guys, but then already, since we multiplied by 1 more power of polynomial of degree d, then there will be some guys. There will be beta 1 tilde over z plus some beta 2 tilde over z squared plus etc. And what are these tildes? If we take the first beta 1 tilde, beta d tilde, they are linear combinations. Linear combinations of this beta d plus 1, etc., beta 2d until 2d. Just by multiplying polynomial and the series, and you can write the combinations. And moreover, these are invertible. So you can express also b d plus 1, b to d as linear combinations of b1 tilde bd tilde. And now we again use the integration. But now we put n plus 1. And again, well, now we have even a smaller function because we multiplied by p of z. So again, our condition star implies that these bks are smaller than 1. And they are again all integers. This implies that bks are 0. And this is for k from 1 to d, sorry, tildes. And since our bd plus 1, b to d are combinations, we obtain that bd plus 1 b to d are zeros. So we got zeros until level 2d. And then we continue this argument. Well, continue the same way, multiply by 1 more power of p, and well, what we need to do, so if we now yes, so we just continue this argument, and we find that all coefficients all bk are 0 for all k. And this completes the proof of the theorem of Poea. Well, again, I find this argument a bit tricky. I like tricky arguments, but I also like to see some theory behind the tricks. And here it looks a bit too tricky to me, but I don't know how to do it better. So again, if someone has some underlying idea behind this, I would be happy if people share it with me. Okay, so this is basically all I wanted to tell now. So Dimitrov's argument is left for the next lecture. So I have like maybe 10 minutes or 9 minutes left. So let me, first of all, are there any questions on this proof? So looks like no questions. So now let me briefly say what we do next time. So on Wednesday. I will prove Dimitrov's argument. And it will be more or less a combination of 3 basic facts. So Schoenemann's inequality, Schoenemann's congruence. And Dobrovolsky used it on level 1, and Dimitrov uses it on level 2, mod p squared. Next, Dubinin theorem about the upper estimate for the transfinite diameter of a hedgehog. And the theorem of Poea that we just proved. so it will be, I think, less, and well, if time permits, so it is not a hard argument. After all the work we're done, Dimitrov's argument really is almost straightforward, just very beautiful. And if time permits, and I think it will permit, I will also prove the theorem of Smith. So if alpha is non-reciprocal, that alpha and alpha minus 1 are not conjugate, then the Mahler measure of alpha is at least theta, where, well, something like one, 3, 2, 4, 7. So where theta is the real root of t cubed minus t minus 1. Well, proof, I said, well, I will not prove exactly this statement. I will prove slightly weaker, which still would imply Lemmer's conjecture for non-reciprocal numbers. That m of alpha is bigger than this number over 4, which is like 128 something. And this is much easier, and but the method is well, one who understands this argument will manage to read Smith's article for the proof of the main statement. So this is what I plan to do next time. And well, I think now I'm basically done, so I think we can finish if there are no more questions.
Yes, I have one more question.
Yes.
Possible.
Yes.
It's a question about the first talk. In your first talk, you proved Dobrovolsky theorem, the one from 1978.
Yes.
And you told us that the one from 1979 is slightly similar, but using more primes than only one.
Yeah.
Now, is there a place where, in fact, this proof is indeed made along the same lines as in 1978 with just using more primes, or does one need many more new ideas?
Well, you see, Dobrovolsky actually, well, I use the prime with this, what we call now in France, interpolation determinant, right?
Yes.
Dobrovolsky himself did not use interpolation determinant. He used interpolation polynomials.
Yes.
But, well, when you study Dobrovolsky's argument, you can easily translate it into the language of interpolation determinants. And actually, I remember that I did it myself when I studied. But then people showed me there was another article by Cantor and Strauss where they formulated Dobrovolsky's argument in terms of interpolation determinants, and this was exactly what I say. So just you take a resultant of f and many f, product of so discriminant of f multiplied by many fp's. You take the discriminant, you estimate it from below.
In which place is it done?
It isn't. There was some article by Cantor and Strauss. Yes, I should check it in Matsenet, but it's easy to find. Yes.
Okay, perfect.
There was also a similar work by certain Louboutin, but I think it is not Stéphane Louboutin, it's some other Louboutin. I'm not sure.
Okay.
Who obtained an optimal constant for that method. They were all about constants. Just
Okay.
yes. But then this interpolation determinant method, I think it could not be extended to more general situations like ellipticals and so on. They had to use interpolation determinants like Laurent, Marc-André, and so on. These people. Okay. So
Yuri,
yes.
I have one question. So when you deduced your first theorem from lemma 2, you never used that those QNs are real, right? You just needed QNs real for the intermediate step.
Sorry, what I use?
The deduction of from lemma 2, your primary theorem, you never used the intermediate polynomials Qns are real coefficients, right?
In deduction
Of the main theorem from lemma 2.
Well, simply no. The point is, formally no, but in the proof of lemma 2, you need
Correct.
it.
Correct. So
You need compactness. You see,
yes.
R quotiented by Z is compact. Yes. C quotiented by Z is not compact.
I see. So that's all.
Yes. So this is what you need.
No, why I'm asking that. So the structure of the that is symmetric is necessary, is it? I mean, one can get into trouble if it is not.
I hear you very badly, Purushottam.
Okay.
There is some echo or whatever, but I
Can
don't
you hear
really
me now? Can you hear me now better? Is it better now? Is it better now?
Yes, a bit better, yes.
No, the fact that your set is symmetric, if it is not the case, the theorem would be false.
Sorry?
If the set were not symmetric, the case...
No, if it is not symmetric, it is obviously false, because...
you can take points, is it?
You need, what you need to define as a kind of symmetric transfinite diameter. The transfinite diameter of symmetrization, and then it will be true, but...
in general,
yeah, but but in this, yes, of course, it is obviously false. You see, you can easily give examples.
Okay.
I'm not ready to produce you an example right now, but it's very easy.
I see.
Yes.
Yuri, but suppose yes. the corresponding, you don't assume that it is strictly less than 1, but it is less than 2, let's say.
Okay, who it?
The transfinite diameter of the compact set is less than 2.
Yes, and then
and K is symmetric.
No, but it will not help you anything. You need polynomial of small norm, of norm smaller than 1. If transfinite diameter is 2, then you cannot get it.
No, maybe not in the integers, but can you get rational ones?
Or rational, sure, you just approximate real polynomial by rational and rational, sure, but it will not help you. They will have too big denominators, and you cannot. You see, all this is based on the discreteness of Z, and Q is not discrete. You see, so you use compactness argument and discreteness argument. Well, the whole Diophantine analysis is based on the ideas of compactness and discreteness, you see. And here is what...
Yeah, and the Polyas theorem will not hold.
Sorry?
Polyas theorem
will not hold also because you're using odd Z is less than 1.
Polyas theorem will definitely not hold. I was thinking that because the transfinite diameter is
scaling, by scaling you can make it
a dilation. So probably rational should be easy to obtain.
No, but it is easy, but it is useless. You see, it will not help you. Well, as long as you do not control denominators, rational numbers are not interesting. You see. Okay. Any more questions?
But the coefficients will not be controlled by the norm, means something like that.
By what?
by the transfinite diameter of the compact set?
I think coefficients you can control the absolute values of coefficients because by interpolation, if the polynomial takes bounded values on an infinite set, then the coefficients must be bounded because you just by interpolation.
So if the transfinite diameter is less than 2, can you get a polynomial with the real coefficients whose denominators are bounded by 2 or something like that?
I don't think so. Yes, no, what you can do, yes. Wait a moment. The point is, no, you cannot, because you should to get it bounded by 1, you should multiply or should do the contraction with coefficient 1/2, but it will not, for the polynomial, it will not produce a contraction of it's not the polynomial multiplied by 1/2, it's the variable multiplied by 1/2.
Yeah,
which means that the corresponding coefficient will multiply by the power of 2.
Yeah.
But divided by the power of 2. No, it's not. Okay.
So let us thank the speaker. If
So,
there are no
thank
more
you.
questions.